Okay, having seen how you can use matrices to solve a system of equations for two unknowns, makes you wonder how you can do the same for system of equations of three unknowns, right? If you have x, y, and z. It turns out that that problem has an answer which is much more complicated than the 2x2 case. So we'll gradually work towards it. So what we need is, if we want to do the same for system of three equations with three unknowns, we would end up with a coefficient matrix that's 3 by 3. And because we solve equations using the inverse, I would be needing the inverse formula for a 3 by 3 matrix. Okay? Now it turns out that this is much more complicated than the 2 by 2 case, so we will have to work towards this gradually. And at the end of the day, rather than actually writing down this matrix and trying to memorize it, we will devise a completely different format, which is called the Cramer's rule. Okay? So that's where we're trying to go towards to. Okay? So this is like the question that we want to touch on later. But for now, let's study this inverse of a 2 by 2 matrix and think about its implications. First of all, this AD minus BC thing, which is in the denominator of all the elements, turns out to be something very important. Okay? So that has a name. So when you have A, B, C, D, and when you write it with using lines like this, sometimes sometimes it's written as dt of A, B, C, D. So whenever you see this or that, it means it's AD minus BC. And this is called a determinant. Determinant of ABC. So a matrix has a determinant, which is AD minus BC. Now, why is it called determinant? What does it determine? Well, it determines whether this inverse exists or not. Why? Because what if AD minus BC is 0? What happens? You're dividing by 0. That means it's undefined. The inverse matrix is undefined. Right? So we have an important thing here. If determinant of A is 0, then A inverse does not exist. Okay, so as an example, 2, 3, 4, 6 inverse does not exist. Because you can see that 2 times 6 is 12, 3 times 4 is 12, and 12 minus 12 is 0. The determinant of this is 0, therefore it does not exist. Now that makes us wonder, what happens if you end up having this type of matrix in a system? What does it mean for the system? So for example, if I had a system of equations having these as coefficients, 2, 3, 4, 6, let's put x, y, and x, y, plus, plus. Let's put something like 1 and 5. Well, here's what it means. If you double this, it's exactly this, isn't it? Actually not. If you double this, the left side is exactly the same. If you double it, you get 4x plus 6y equals to 2. And that doesn't agree with this one. So what does that mean? What does that mean?
It's not equal.
So,
It does exist.
huh?
It does exist. Something number.
Say it again.
It doesn't exist.
What doesn't exist?
There's no solution.
There is no solution. Okay, there is no x and y. There are no x and y numbers that would satisfy both of these equations. I mean, if there were, then you couldn't have 2 and 5, two different things. I mean, how can you have a single pair of numbers at one time when you calculate it gives you 2 and another time it gives you 5? That's impossible. Okay? So, in such a case, that there won't be any solution at all. Okay? Now, what if this was 2? Then they're saying the same thing. What does that mean? No, the determinant of this matrix is still 0. Yeah. We're still on this case. I'm talking about this system. What can you say about this system? It's like this. You're initially given 2 equations for 2 unknowns, right? So you're happy, you want to solve it. But then, as soon as you multiply the first one by 2, you realize that what you thought were different clues about 2 unknowns are actually the one and the same thing. So in effect, you're given 2 unknowns, and you're provided with only 1 clue. What does that mean? Rather, it means that there are infinitely many solutions. There are infinitely many pair of numbers that would satisfy this. So one example would be, let's see, -3. How does that work? -1 and +1 is a solution, right? That will satisfy both. Another example will be 3 and 2 and -1. That's another solution that satisfies both. Right? Another example would be 5 and -3. It will also satisfy. So you have infinitely many pair of numbers that would satisfy this system. There's just a lot. Okay. So we're still happy because one of the worries was, if the inverse doesn't exist, then does that mean we can't solve it using the matrix method? Well, yes, we can't solve it using the matrix method, but it's not that bad because that only means that the equation you're given is sick in some way. It's like either there's no solution, or if there are solutions, there will be infinitely many solutions. So that's what it tells us. Okay, so in terms of systems, if the determinant is 0, then we know that the solution either doesn't exist or there are infinitely many solutions. Maybe I should write that. Okay. So if determinant A equals to 0, then AX equals to B has no solution or infinitely many solutions. Infinitely many solutions. So that's why determinant is important. Okay, going back to 3 by 3, then the first thing that we should think about in working towards to an inverse of a 3 by 3 would be finding an analog of such a thing for 3 by 3. Okay? So let's try to define 3 by 3 determinants. So now our question is, what is the determinant of a 3 by 3? How do you calculate that? And of course, you can do the following. You can do the same exact thing that we did before. You can write down x, y, z, omega, alpha, beta, gamma, delta, eta, or something, and then you set it equal to the identity matrix, you multiply it, and you solve this huge system. Okay? And when you solve it, at some point you'll see something like this happening. All the denominators are exactly the same, and then on the top it's just some jumble of something really complicated. Of course, I can't possibly do it here. That's going to take too much time. So I will just tell you the result. Okay? And even just the determinant is so hard to remember and write down. People devised a system to write down the determinant of a 3 by 3, which actually is true for 4 by 4, 5 by 5, and so on and so on. Okay? So what is the determinant of 3 by 3? So here's how it goes. Actually, I have to give you this in steps. Okay? So first, what you have to know is there is something called the checkerboard of signs. Checkerboard of signs. It's like basically a checkerboard, but made up of signs. Okay? And then given a, so that's the first thing that you have to know. And then given a matrix, there is also something called a minor matrix. Which is, if you're given a matrix, the matrix obtained by, say, let's pick a row. Let's pick the second row and the third column. And this matrix that you have, A, B, G, H, this matrix has a name. It's a matrix, it's a submatrix, it's a minor matrix, obtained by deleting the second row and the third column, right? So we put that as a subscript. So if the original matrix is A, when you see this matrix A sub 2, 3, that means it's a minor matrix obtained by deleting the second row and the third column. Okay? So these are the two things to know before even writing down what determinant of 3 by 3 is. Right. Okay. And then it goes like this. The determinant of A, B, C, D, E, F, G, H, I is given by a process called a row expansion. Row expansion. Which is done by the following procedure. First, you pick a row. I'll pick the first row because that's often the case. A lot of times people pick the first row. There's some other cases, we'll discuss that later, but if I choose the first row, this is what you do. First, you pick the element, put it here, okay. And you write the determinant of the minor matrix obtained by deleting the row and the column containing the element. So what is that? It's this one, right? So E, F, H, I. And you take the determinant. And then you apply the sign given by the checkerboard of signs. So you see how these two are applied here? Okay. And then you do that for each element. So now let's go to the second element. We're doing row expansion, right? I picked the first row. So A was the first one. But now the second element is B times what? Determinant of what?
D, F, G, I.
Yeah. So you take this away, that away, D, F, G, I. D, F, G, I. And what do I put? Minus. Okay. And plus, yeah, it's plus because the checkerboard of signs says plus times C times what? D, E, G, H. That's the determinant. Okay. Now, how do you calculate this? You just draw this fish shape, right? So you have A times EI minus FH minus B DI minus GF plus C times DH minus G. And if you multiply everything out and organize nicely, that's the determinant. Now what's interesting is whether you pick the first row or the second row or third row, or whether you pick the first column or second column or third column, as long as you do the exact same procedure, the end result will be the same. So not only it gives us, this procedure gives us the formula for the determinant, and I mean, think about it. If you were to actually expand this and you had to memorize this, wouldn't that be really hard? It would be really confusing, right? So writing it in this form provides a good way to remember what this last thing is, but it also gives us a convenience of allowing us to choose whether you want this or this or this row, or we can even expand by columns. Okay. Now, why is this good? Well, that's because if we had lots of zeros, that means we want to pick that column or the row. So let's think about the following. It says, say 3, 2, 1, 5, 0, 0, right? 0, 2, and negative 1, 0, 7. So let's think about this. And we had to calculate the determinant. What would we do? We would expand in what?
Column 2.
Second column, right? Because it has 2 zeros, that means I only have to do 1. Right? So when you want to calculate, I would do, this one has a minus, right? So it's minus 2. And then the minor matrix is 5, 2, negative 1, 7. And then the next one has plus, but it's 0. So plus 0, I'll just write what we're supposed to write, 3, 1, negative 1, 7. But we don't care because it's 0 times something. And this will have a minus again, but we don't care either, so because it will be 0 times something. Therefore, the determinant of this will be 5 times 7, that's 35, minus negative 2, that's 37, times negative 2, that's 74, right? Negative 74. So what does this tell us? It tells us that this matrix does have an inverse because this is non-zero. Yes?
So why do you start with the negative this time, though?
Oh, because we're doing this.
Oh, okay.
Yeah, it's minus plus minus.
So whatever one you choose is what other
Yeah,
signs?
so,
Okay.
so the checkerboard of signs must be applied when you
Okay.
calculate this. Any other questions? So that's how you calculate 3 by 3 determinants. Now, one more thing. I mean, you might wonder, why do we have to observe this sign? Can't we just remember that the sign alternates because we only care about whether it's 0 or not? Well, it turns out that later on, this determinant has a lot more meaning than just telling us whether the inverse exists or not. It has the meaning that when you use matrices to transform domains in three-dimensional space, the change of volume is explained by the value of the determinant. That's something that I've yet to explain, so it's something that you wouldn't understand at this point, but that's why we actually want the value of the determinant too. Also later, we will be doing something called eigenvalues and not here, but in your differential equations class, you'll be doing eigenvalues and eigenvectors there, this is used in a more meaningful way. So it's really important to learn about determinants. I just want to talk about this one final property of the determinant. Determinants have the property that if you have products of two matrices, taking the determinant of the product is same as taking the determinant of each matrices and multiplying them. So it has this nice property, and it has its uses too. So let's say you made a product of two huge matrices and you weren't too sure if you made a mistake or not. One way to check would be calculate the result, calculate the determinant of the result that you had, and calculate the determinants before you had, and see if they match. If they don't, that means you made a mistake somewhere. Okay? So this is a good way to check. All right, that's all we have for today.